Good morning and good afternoon, everyone. My name is Brian Foster. I'm a content director here at PingCap, and I'll be your MC for today's event. In today's hands-on workshop, we have Stephen Thorne, Principal Solutions Engineer at PingCap, and he's going to show you how TiDB's distributed SQL engine, Raft-based replication, and online DDL keep payments and ledgers running through traffic spikes, releases, and node failures. We'll also walk through how to ensure zero downtime via seamless online rolling upgrades with uninterrupted client sessions. Here's a high-level view of what we'll be covering in today's workshop. We're going to kick things off with an overview of TiDB and how its architecture delivers things like horizontal scale and strong consistency for FinTech workloads. We'll then show how TiDB uses Raft leader election and automatic failover to preserve availability during incidents. And finally, we'll wrap up with a hands-on lab focused on how to achieve zero downtime for a database, in this case, TiDB, during a data center or availability zone failure. Now, before we get started, for everyone tuning in, please feel free to drop your questions directly into the chat window here. We'll be sure to answer them during the short Q&A portion at the end of the webinar. Now, let's get ready to have some fun. I'd like to hand the reins over to Stephen. Stephen, the floor is yours.
Thanks, Brian. Hey, everyone, thanks again for joining today. Like Brian said, I'm Stephen. I'm a solution engineer at PingCap, and my role is to help companies modernize their data infrastructure with distributed SQL. Today's session is zero downtime upgrades with TiDB. We'll explore why zero downtime is critical, especially in industries like FinTech or if your company has a SaaS product, how TiDB's architecture enables rolling upgrades without service interruption. We'll touch on a real-world case study and a demo of an online upgrade. So specifically, I'm going to talk about the cost of downtime, upgrade strategies, TiDB's architecture, the demo, case study, and then a summary and time for Q&A. So first, a little bit about me. Like I said, I'm an SE at PingCap. Previously, I've been a solution engineer for Percona, which is an open source database company focusing on MySQL, Postgres, and MongoDB. I was the founding SE at a Kubernetes troubleshooting startup, and I've also supported the government in a variety of different roles. First, let's talk about the obvious. Why downtime is scary. So what is downtime? Downtime is any period during which a system, service, or application is unavailable or not functioning. In today's always-on world, users expect services to be continuously available. Downtime has some serious consequences. You can lose revenue, erode trust, and break regulatory violations. Even a short outage can cost millions of dollars. For example, and I know this is extreme, but it definitely highlights the point here, in 2018, Amazon had a 75-minute outage, costed them an estimated $90 million in lost sales. That's roughly $1.2 million per minute. Outages also erode user confidence. Customers who experience failed transactions or any unavailable services lose trust, and they may switch to competitors. Repeated downtime can ruin a company's reputation and really set you up for failure. Many companies also have SLAs promising high uptime to customers, and regulators are imposing resiliency requirements. For instance, the EU's DORA Act requires banks to restore critical systems within 2 hours of an incident, and that went into effect January of this year. So given these stakes, traditional upgrade methods that require downtime just don't cut it anymore. The expectation is always on operations, so even planned maintenance should not interrupt service. Luckily, TiDB addresses all major causes of downtime, both unplanned outages and planned maintenance, including online and non-blocking schema changes. But today, we're going to focus specifically on how TiDB eliminates downtime during upgrades. Now that we understand the cost of downtime, let's examine common database upgrade strategies and their trade-offs. First, we have in-place upgrades. This is the simplest approach. You shut the database down, you apply the upgrade, and you start it back up. While this is easy to execute, the obvious problem is downtime. Your application is completely offline during the process. You also need to carefully schedule maintenance windows, which can be during late nights or weekends, which no one likes, so that's a burden operationally. In short, in-place upgrades are non-starter for mission-critical systems. Next, we have blue-green deployments. In this approach, you maintain two environments: blue, the current production environment, and green, the new version. You set up a new green cluster with the upgraded database and replicate data from blue to green in real time. Once they are synchronized, you switch over by directing applications to the green cluster. This method aims for near zero downtime, though not entirely zero. Challenges with this strategy include replication lag, the complexity of dual writes, and the need for careful coordination during cutover. Managing two-fold environments also incurs significant cost and complexity. So while blue-green deployments can reduce downtime, it adds a lot of operational risk and overhead. Finally, we have rolling upgrades. This is the ideal solution for continuous service. In a rolling upgrade, you upgrade the database one node at a time, while the rest of the cluster continues to handle application traffic. There's no need for a separate environment. Each node is taken out of service, upgraded, and then brought back online until all nodes run the new version. If done correctly, the database remains available throughout the entire process, enabling zero-downtime upgrades. This method requires a distributed database architecture that supports online node-by-node changes, and that's exactly what TiDB is built for. Now, let's quickly touch on TiDB's architecture and see how those make rolling upgrades possible. For those of you who have not heard of TiDB, I'll quickly go over what it is in the architecture. So TiDB is an open source distributed SQL database designed with continuous availability in mind. It separates the system into layers and replicates data to prevent single points of failure. TiDB supports massive scale. And when I say massive scale, I'm talking millions of tables, petabytes of data, and millions of queries per second per cluster. TiDB's architecture separates the SQL processing layer from the storage layer with a distributed metadata layer for coordination. This diagram highlights TiDB's main components. Again, we have our compute or SQL layer. These are our stateless TiDB servers or TiDB nodes. And then we have a storage layer or storage cluster that contains two components. The first is TiKV, which is a distributed key value storage engine for transactions, and TiFlash, which is an optional columnar storage engine for analytics. And then we have the PD cluster, which is for metadata and scheduling. Each component can scale horizontally and is deployed in multiple instances for fault tolerance. The TiDB server layer is a stateless compute layer, which is shown in red here, and a few key points about the TiDB servers. First, every TiDB node is both a reader and a writer. This allows you to scale both reads and writes into several million queries per second per cluster. TiDB nodes handle SQL processing and execution, that's for both reads and writes, but they do not store any persistent data themselves. They're stateless, meaning if a TiDB node goes down or restarts, no data is lost. It simply reconnects to the cluster. This stateless design allows TiDB nodes to be added or removed horizontally for scaling without data rebalancing. All TiDB servers are equal in function, and clients can connect to any TiDB server. Typically, you'd have a load balancer or proxy in front of it, like TiDB's proxy called TiProxy, and that's to distribute traffic among the TiDB nodes. Additionally, TiDB servers can be spread across multiple AZs or data centers, so if one node or even an entire AZ fails, the TiDB nodes still serve the application. And that's also true for the storage layer here. So the first part of our storage layer is TiKV. TiKV is the distributed transactional storage layer, which is depicted in blue-green here. It stores all the table data in a transactional key value format. Data is split into many ranges, called region, and each region, and thus each piece of data, is replicated multiple times across different TiKV nodes. It's replicated by default with 3 copies. TiKV uses the Raft consensus algorithm to maintain those replicas and to ensure strong consistency. One replica of each region is a Raft leader, which handles the reads and writes for that region, while the others are followers. If leader fails or goes offline, the followers will automatically elect a new leader. This mechanism is what provides high availability for storage. Even if one TiKV node is down, its replicas and other nodes take over with no service interruption. Also, TiKV is horizontally scalable. You can add more TiKV nodes to grow storage capacity or throughput, and TiDB will rebalance regions across the nodes. TiFlash, which is shown in purple here, is our optional columnar storage engine. TiFlash nodes replicate data from TiKV, again, that's the row data, into a columnar format suitable for analytical queries. This replication is asynchronous but near real time. TiFlash allows heavy analytical queries to be run without impacting the transactional workload. Again, TiFlash is optional to deploy and use, and the TiDB nodes has a TiDB query engine, which automatically routes queries to either use TiKV or TiFlash as needed. Next, we have our placement driver, or PD for short, which is shown in the blue circles here in the diagram. PD is the brain of the cluster. PD stores the cluster's metadata and handles the global coordination. It's responsible for functions like allocating global timestamps for transactions, managing cluster configuration, and making decisions about data placement, such as balancing the load or handling failovers. In a production environment, there are going to be at least 30 PD nodes forming their own group for high availability. That's also scalable as well. Some of our customers will actually deploy with 5 PD nodes. Only one PD leader is active at a time, but if that leader is upgraded or fails, a new PD leader is instantly elected. PD being redundant means the cluster can keep functioning if one PD is down during an upgrade. To summarize the design, TiDB separates the compute from storage and replicates everything important. Compute nodes, the TiDB nodes, are stateless and can be restarted freely, and storage nodes, TiKV, maintain multiple replicas via Raft so that any single node can be taken out without bringing the system down. This design underpins TiDB's ability to do rolling upgrades. Next, I'll quickly touch on the upgrade process and how TiDB ensures continuity during each step. So TiDB performs a rolling upgrade by updating one component at a time, with the rest of the cluster handling the load. The guiding principle is that at any point, the cluster remains available to serve both reads and writes. First, we upgrade the TiFlash nodes. That's if they're present. Like I mentioned, this is optional to deploy. Since TiFlash replicas are a Raft learner role, meaning they don't vote in leader elections, we start here and update them one by one. Upgrading a TiFlash node pauses its sync briefly, but there's no impact to the transactional workloads. Next, we upgrade the PD nodes one by one. Because there are multiple PD nodes, we always keep a majority online, thus you have quorum. TiDB is going to transfer the leadership from the PD nodes away from the one being upgraded, so a different PD node serves as leader while one is restarted. We then upgrade the TiKV storage nodes, and this includes leader evictions. This is the most critical step, as TiKV holds the data. For each TiKV node in turn, we first proactively evict its region leaders, meaning we transfer leadership of all the Raft groups or regions on that node to other replicas. This means that when we stop a TiKV node, it's no longer the primary for any data. Other TiKV nodes have already taken over those responsibilities. With followers now serving those regions, the node can be taken offline without impacting read or write availability. We then upgrade the TiKV node's binary and bring it back up online with the new version. The Raft groups will catch up to the data on that node, and it can even take over some of the leader roles eventually while the other nodes are upgrading. We go through this step and repeat it for each TiKV node one at a time. Throughout this process, a majority of replicas for each region are always up. Because there's a quorum of replicas available, the cluster keeps serving reads and writes without any interruption. Next, we upgrade the TiDB compute layer. Since TiDB nodes are stateless and behind a load balancer, we can take them out one by one. Before we're starting a TiDB server, new connections are routed to other nodes so there's no interruptions from the queries hitting the system. If you're using TiDB's proxy, again, it's called TiProxy, it's going to automatically migrate active sessions off the node that's about to be upgraded. This ensures that clients remain connected. Lastly, we upgrade the monitoring and tooling. So this sequence of going from TiFlash to PD to TiKV to TiDB and the monitoring is designed to minimize risk. At each stage, we either leverage redundancy or the stateless nature of components to avoid downtime. I just want to emphasize the core mechanism here. Raft-based replication and consensus is what makes this all possible. TiDB storage nodes use Raft to agree on data. During an upgrade, Raft allows us to hand off the leader role from one node they're upgrading to another node. This is a quick diagram showing how it's done node by node, going from the old version to new version. All right, I'm quickly going to switch screens here and go through a quick live demo. Again, if you have questions, feel free to drop them in the chat. Okay, a quick orientation. So this is our monitoring tool we're using today. This is the TiDB dashboard. I'm specifically looking at our queries per second on the system. As soon as we started the lab, I started running some scripts on the system for both reads and writes. So if you see here, I have some inserts and selects on the system. It's continuously uploading data into the TiDB cluster. And I have 2 tabs which are showing the actual nodes that are generating load in the system. This is the write traffic to the system, and this is the read traffic to the system. Right here is our TiDB cluster. This is a tool called TiUp. It's a command line interface management tool for a TiDB cluster deployed on virtual machines. In here, you can see that we're on TiDB version 7.5.4. We have, I think it's 11 nodes. We have some monitoring components. We have our PD, our TiDB nodes and TiKV nodes, and we have our TiProxy. If you look at the status column here, everything is in an up status. And this L here for the PD node means it's the leader of the PD group. So we have traffic on the cluster. I'm going to execute an upgrade of the cluster, and we're going to monitor the traffic during this process to see if there's any service interruption. So what it's doing now is it's downloading all of the new versions for the different components for the new TiDB cluster here. So you're going to see a lot of lines where it's stating that it's downloaded the components. We have Grafana, we have TiKV, PD, TiDB, Prometheus, and Alert Manager. And this will take just a minute here. Looking back at our dashboard here, I wouldn't expect to see any service interruption because all the nodes are still online here. But just to monitor it, we still have continuous traffic on the system while it's downloading, which is good. And if I look at my scripts here, I still have write traffic in the system and read traffic as well. And after this downloads all the different components, it's actually going to go through and configure everything automatically. As you can see, I simply had to run two commands. One was to point tie up in a new version, and the second was to execute the upgrade. So very, very easy to actually manage this. There's a lot of lines here that are just talking about the different configuration of the services before it upgrades everything. And it's actually going to do the node exporters first here, and then it'll go through and do PD. Okay, it's started on PD now here. So you can see how quickly these are restarting. And because our dashboard is actually on the PD node, I just need to sign back in. Okay, so PD is successful and it's done. It's now going through and doing the TiKV nodes. So like I mentioned, all of the leader nodes of those Raft regions are going to be moved to other TiKV nodes before upgrading, so there's no service interruption. And that's what these lines are stating here. So still waiting for 17 stored leaders to transfer. Store is just another term we use for TiKV nodes. You can see that these numbers are decreasing, which is great. Those Raft groups are being transferred to different nodes. The leader role is at least. And once this goes down to 0, it will restart the TiKV node, and I'll go through this process again for the other two TiKV nodes in the cluster. This is definitely the longest part of the upgrade here. This is a pretty small cluster here with only 3 storage nodes. Some of our customers have tens, if not hundreds, of TiKV nodes because it supports pretty massive scale here. So while it does take a while, it's not impacting their application. It's happening in the background. So that TiKV node is done. This one here is done. It's on the third one now. And again, we still have consistent traffic on the system, which is great. TiKV is done. It's going through TiDB now. So it's going to manage the connection. TiProxy is going to migrate the active sessions on the one TiDB node to the other one, restart it, and then move them back to the TiDB node that's just upgraded, and restart the second one here. But look at our command line here. We have no errors. We're still getting inserts to the system or writes, and we still have reads or selects on the system as well during this process. And that is further supported by our monitoring tool here as well. Okay, so one TiDB node is updated. It's doing the second one here. And then we'll hit Prometheus, Grafana, and Alert Manager, and it should be done after that. So TiDB is done, Prometheus is done, Grafana, Alert Manager, and we wrapped up. Okay, so let's check to make sure that we are on the new version here and double check that there's no service interruption. Okay, we are on 8.1 here, which is great. We have a status of up for everything, and we have our 11 nodes. Let me reload this page here. And we have a slight dip of 1 to 2 queries per second in this, but no interruption. So that's great. All right, let me switch back over to the screen and we will close out with 2 more slides. And then we can go to any questions we have. So let's quickly look at a reference architecture to see how TiDB enables always-on real-time FinTech applications. So in FinTech and any other high-performance industries, obviously every millisecond matters. No services can be afforded to be offline. Things like payment processors, banks, wallets, brokers, and lenders, they all need a single transactional core that scales as demand spikes, stays available during failures, and meets strict SLAs. If we look at this diagram here, you plug everything into TiDB and you treat it as an operational data layer. So that could be things like system of records, systems of engagement, and any kind of external data feeds. You treat TiDB as a unified transactional backbone, ingesting operational data, keep it safe and consistent in TiDB and highly scalable, and then you fan it back out to all of your other applications. I know that I mentioned this before, but I'd like to reiterate it here. TiDB handles massive scale, so that's millions of tables, petabytes of data, and millions of queries per second on the cluster. And that's what enables you to treat it like a single operational backbone, replacing often many different database systems or a sharded database environment. Finally, let's look at a real-world case study. So Plaid is a leading FinTech platform that connects apps to users' bank accounts. They were on Aurora MySQL, and they outgrew its capabilities. They had around 450 Aurora MySQL servers, so a pretty large environment. Routine upgrades were so labor intensive for Plaid that a simple upgrade from 5.6 to 5.7 consumed 2 engineering quarters, and even standard failovers introduced downtime. And that's really tough for a team that was targeting 5 nines of availability at the database tier. After they went through their evaluation, they landed on TiDB and chose TiDB for its online upgrades, online schema changes, and massive scale. Again, TiDB enables online schema changes and rolling upgrades without taking services offline. Post-migration to TiDB, the benefits were really clear to Plaid. The maintenance became non-destructive. They didn't have to do any more 2 a.m. cutovers. Operations were simplified as they were managing a few scalable TiDB clusters versus 450 Aurora clusters. And developer velocity improved thanks to online DDL and zero-downtime upgrades. So in short, TiDB helped Plaid meet extreme scale and reliability needs while keeping the lights on, showing that zero-downtime upgrades aren't just aspirational, they're practical and pay off. So recapping what we talked about today, upgrades on TiDB are rolling and online by default, leading to zero-downtime operations. HA is built in by default. Data is safe and consistent during all operations. The business wins with protected revenue and happier customers, and then engineering wins with lower complexity, automatic failover, and faster adoption of features. Today, actually used one of our labs off of our website, labs.tidb.io. I know I did this in a terminal, but on the website here, all of our labs are browser-based, which makes them very easy to get started and use. We have over 40 different labs here. So online rolling upgrades is one. Online schema changes is another. Just a lot of different TiDB features and different labs here. This is free to sign up and use. So if you guys want to get started and play with TiDB, there's a lot of different ways to do that. Labs is one of them. We also have a free serve list here on tidbcloud.com, which is a great way to have a cluster that's already up and running to point your application at it and start testing with TiDB. And Brian, if you have any last saved rounds. If not, I will see if there's any questions from the group.
No, I think you covered it with the TiDB Labs. Definitely encourage folks to kind of check that out. Again, very simple. Just go to labs.tidb.io. We have a lot of different types of labs, ranging from scalability to very specific deep dives into specific technology aspects of our technology. So definitely check those out. But yeah, Stephen, it looks like we did have one question come in. Let me read that one to you. If I have 2 clusters for a failover scenario, a primary and DR cluster, that's synced by TiCDC, which cluster should I upgrade first? And will there be interruption for the CDC sync?
Um, there should not be interruption, depending on which one you upgrade first. Um, there's probably a lot of factors that go into that. I imagine you'd probably upgrade the DR one first, and then your main one. But if you want to find me on LinkedIn or shoot me a note after this, I'm happy to double check on that, to get you a more robust answer. But that's a great question.
Yeah, I thought so as well. Let me see here. So yeah, I have one here. So, how do you verify, during a rolling upgrade that client sessions aren't dropped and P95, P99
Mhm.
stay within SLOs?
Yeah. Great question. We have a pretty robust set of monitoring tools. So I touched on one today, which is TiDB Dashboard. That is our own monitoring stack. We're using, metrics from Prometheus, exporters into the dashboard. We also have a ton of Grafana dashboards that are very robust. So there's a lot of different ways to monitor traffic during an upgrade to ensure that there are no breaches, there's no data loss or anything like that. We have dashboards for literally everything, so it's very easy to monitor.
Awesome. No, thanks for providing that insight. Uh, Another question here. When a TiKV node fails mid-transaction, like what actually happens? And how can you minimize, a performance ripple, during that window?
If a transaction has failed on a TiKV node, um, I think it would go back to the application to depend on what the behavior is, what it would do, but it wouldn't commit. So TiDB is strongly consistent. So if there's any kind of error during that, it just wouldn't commit the data. And I imagine the application would probably retry at that point. But
Got it.
there's not going to be any half transactions or weird like that because it is strongly consistent.
Got it. Got it. No, that makes a lot of sense. Let me just see here. One more question here. How do you forecast capacity for multi-tenant FinTech workloads without over provisioning?
Yeah, that is a very good question. Typically, what we're doing is we're looking at the cluster itself. We're using the monitoring tools we have to look at the actual traffic. If we can break that down to like per tenant, that's great. We then would see, what is your expected growth, and help you size the cluster to that growth as it scales. So that would be on our like dedicated version of the cluster. We also have a serverless offering, and we also have like a self-scaling version called TiDBX, which is going to auto scale to traffic as well. So it kind of takes that variable out of the equation. So there's two different ways to do it. If you're on a dedicated cluster, we'd use monitoring to look at the actual traffic on the cluster and size appropriately. And we also have a serverless or TiDBX, which does auto scaling for you.
Awesome. That's excellent. No, thank you very much for kind of going into that, kind of providing additional details. I think, again, I think this has been a great, great presentation and deep dive. So again, I want to thank everyone, for attending today's hands-on lab. We hope you enjoyed the content throughout. We're able to learn a ton. Again, definitely check out our lab's content for more. I think you'll really enjoy it. We'll be sure to make a recording available to everyone who registered for this session in the coming days. And separate from our labs, if you'd just like to learn more about TiDB and its capabilities, just please visit us at tidb.io. So with that, I'd like to thank you all and close out today's session. I hope everyone has a great rest of their day.
Thanks, everyone. Appreciate it.
Take care.